All right, so Bismillah Rahman Rahim. So let's start introducing Fourier transform. Couple of videos I made that was based on Fourier series, and normally we know that Fourier series is generally used for periodic signals and to find out the frequency component which are there in a periodic signal. So that was the definition of Fourier series, which was given as x of t is equals to n as it goes from negative infinity to positive infinity, x of n e to the e to the positive j 2 pi n f naught t dt. This is one of the forms. This is actually a complex form of Fourier series where I'm just where x of n, I'm just writing these things down so you would know, is 1 over t x of t e to the negative j 2 pi n f0 t dt. This is one of the forms that we looked at of Fourier series. This is actually a complex form of a Fourier series, and I think I've made a video on how do we came up with and we changed the derivation. We actually changed from a trigonometric one, from sine and cosine form, to this particular form. So we're going to use this. So this is actually the definition of Fourier series. Now we're going to use this definition of Fourier series and we're going to drive Fourier transform. And there are a couple of things that I need to consider. Okay, I know that generally Fourier series is for periodic signal, but when I have an aperiodic signal, which means let's think of it just like a pulse or a signal that does not repeat itself, how we're going to actually do, I mean, what do we do? So generally the rule of thumb is this: for periodic signals we like to use Fourier series, and for aperiodic signal where the signal does not repeat itself, we're going to use something called Fourier transform. Fourier transform actually derived from the definition of Fourier series. So what we're going to do, we're going to derive Fourier transform from the definition of Fourier series. All right, so we're going to consider a few things. First thing we're going to look at, we're going to assume first that I have a periodic signal which is like this. All right, but we're going to assume this. We're going to assume that this aperiodic signal, which means it's a non-repeating signal, it's going to repeat itself after a very, very long time. All right, so this is my actual signal, which is an aperiodic signal. Let's call that signal xp of t. So we're saying this: these two elements that we are seeing, let's just call them xp of t. What it is a periodic extension of my signal. What it is, it's actually a periodic extension of my signal. And what is it that I'm saying is this: that yes, it is a periodic signal, but this signal, it is an aperiodic signal, but we're making one assumption, that it's going to repeat itself after a very, very long time. After a very, very long time. All right, I hope you're getting this. I hope you're understanding it. So this was my actual signal, which is an aperiodic signal. We're making a periodic extension of this signal in both the negative side and positive side, and we're calling it xp of t. And basically what we're saying, we're making an assumption that this signal, yes, in reality it's a aperiodic signal, but it's going to repeat itself. It's going to repeat itself definitely, but after some amount of time, after a very long amount of time, but it's definitely going to repeat itself. So this xp of t is going to be my n. So I'm just simply applying this definition of Fourier series, n as it goes from negative infinity to positive infinity, x t minus nt, where n can be 0, plus minus 1, 2, and so on. All right, so it's a periodic extension of the signal. I hope you're getting it. So now we're going to make this assumption that we're going to take a periodic signal and we're going to drive a Fourier transform based on the definition of Fourier series. So here's what we're going to do. We're going to take our xp of t. So I'm going to take my xp of t and I'm going to write the definition. So this is going to be n as it goes from negative infinity to positive infinity, right? X of n, which is just this definition, e to the j 2 pi n f0t. Right? So far so good. All right, that's what we're gonna do. Now, what is the definition of xn? The definition of xn is given inside of this, isn't it? This is the Fourier definition. This is the Fourier definition. Right? In Fourier series, we came up with this. This is the main equation, and x of n is equals to 1 over t x of t, whatever that signal is, e to the negative j 2 pi n f0t. So what we're going to do, I'm going to take the summation out. That is n as it goes from negative infinity to positive infinity. All right. I'm going to put a bracket inside of it. In place of x of n, I'm going to put this definition. All right. So in place of n, this is going to be x 1 over t. X, what is my signal? We're actually looking at a periodic extension of this original signal, which is xp of t. E to the negative j 2 pi n f0t dt, whole thing. So this is my x of n term, and then I'm going to bring out my kernel, which is e to the j 2 pi n f0t. Are we good so far? So I'm just going to make few replacement here. I'm going to rewrite this as n goes from negative infinity to positive infinity. All right. I'm going to change 1 over t as f naught, my carrier frequency. This is going to be t. It's going to remain the same, xp of t, e to the negative j 2 pi n f0t dt, whole thing, e to the j 2 pi n f0t. All right. So far, are we good? So all right. So let's look at this particular definition, and based on, so what we're trying to do, we're trying to drive Fourier transform using the definition of Fourier series. All right. So I have this equation, and now this is what I'm going to do. I'm going to assume a couple of things. All right. I'm going to assume a couple of things, and based on those assumptions, I'm going to actually manipulate this equation a little bit. All right. So first, I'm going to do this. I'm going to take t as it goes to infinity. All right. This is the first assumption that I'm going to take. All right. Now I'm going to use this condition where I'm going to take my t, which is actually my period of that signal, is getting very, very big. Same condition, which means the signal is repeating itself after a very, very long time. This is what I'm assuming. All right. By taking this t, since I'm looking at a periodic extension, couple of things will happen. There's a couple of things this will happen. When I take t, so as t goes to infinity, which means my period is getting bigger, couple of things will happen. First thing will happen is this. The first thing, xp of t would become x of t, isn't it? As t is going to get bigger, my periodic extension would just act like a normal signal, isn't it? Isn't it? As my period is getting bigger, my periodic extension, they will act as a normal signal, like a aperiodic signal. That's the first thing that will happen. Second thing that will happen is this. My f's, my frequency will actually become df's. As my frequency is getting bigger, check this out. As my time is getting bigger, my frequency is getting lower and lower. So what am I saying is this: the separation between my sinusoidal waves is not integer multiple anymore. It's a very smaller value. It's a differential value. I hope you're getting my point. What I'm trying to say, as my t is getting bigger, what is happening to my frequency? My frequency is going down. How small is going down? You don't know. It's not going down as an integer value. It's actually getting smaller. This is the second thing that will happen. All right. Now, what will be the third thing? These NFOs, This FO corresponds to this term. All right, I hope you're getting it. I hope you're getting it. This is very important. And these NFOs, this is actually these kernels. All right, NFOs, which are on top of these kernels. Now, what that means is this. What that means, these NFOs will convert into Fs. These NFOs. Now, what it means? What does it mean as T is getting bigger? Now, when the T is getting bigger, it's saying you can take as many steps as you want. All right, means you can take as many steps you want. All right, these NFOs, as the T is getting bigger, this is getting smaller and smaller, and you can take as many steps as you want. All right, this is what will happen. So as T is getting bigger, and the fourth thing is, when T is going to get bigger, the summation, which is going from negative infinity to positive infinity, this will change into integration from negative infinity all the way up to positive infinity. These are the couple of things that will take place when I start doing this. Right, when the T is getting bigger and bigger, couple of things. This periodic extension will actually become your actual signal. The FOs will become DFs, because when the frequency is going down, you can take, like, now is that integer multiple, the separation is actually much smaller. These separation, you can take as many steps you want in order to make that a fundamental frequency, which is F, and these summation will actually become your integration. All right, so what type of effect you will see on that equation? Now just quickly look at it. So we had a signal, we had an equation which was something like this. So n, as it goes from negative infinity to positive infinity, all right, so this was FO, all right, dxp of t e to the negative j 2 pi n f0 t, whole thing, e to the j 2 pi n f0 t. Now when I start making these assumptions, a couple of things will happen. Now this whole thing, first of all, I'm going to change this. All right, I'm going to change it with black. All right, this summation will become what? Integration. That integration is going to be from negative infinity to all the way up to positive infinity. That's the first effect that you would see. Now these F naughts, would become what? Your DFs. So let's do this a little bit later. So this one's going to be, and this xp of t is going to be t as it goes from negative infinity to positive infinity. This x of p of t is actually becoming your x of t. All right, this kernel NFOs will become e to the negative j 2 pi f t. All right, and this would become, of course, dt. We're looking at it with respect to this whole thing multiplied by e to the j 2 pi ft. And remember these, this term which was your FO, that is becoming your DFs, and this would have your DF. So if you were to look at it closely, we have actually came up from Fourier series. We actually drive the equation for Fourier transform, and this is what it is. Okay, let's look at it individually, because you're probably not seeing it. If I were to just look at this particular term, what does it look like to you? What does it look like to you? I'm gonna change. I'm gonna write it separately. I'm gonna write it here. I'm gonna write them here. So if I were to look at this, this would be x of f, because what? This is actually giving me a Fourier transform of a signal, which means taking this signal in time domain and converting them into a frequency domain signal. So this is going to be x of t. You're going to take your signal e to the negative j 2 pi ft dt. So this is your actually a Fourier transform. This equation is your Fourier transform. Now let's look at the outside. If this whole thing is x of f, then once you're given a signal which is in frequency domain, you can convert that into time domain, isn't it? So this would become x of t if this whole thing is x of f. Can you guys see this? I hope you can see this. If this green thing is x of f, then x of t is going to be what? Is going to be x of f times e to the j 2 pi ft df, isn't it? And this whole thing is going f as it goes from negative infinity to positive infinity. Isn't that amazing? So this is the definition of Fourier transform. And this is what? This is what? This is inverse Fourier transform. Fourier transform. All right. So this is the definition of Fourier transform. This is the definition of inverse Fourier transform. We came through from Fourier series. You probably have seen it. The other way of looking at it. So the other way of looking at it, you might have seen it something like this in other type of textbooks where you have x of omega, everything in terms of x of omega, that is going from positive infinity, x of t e to the j omega t dt, and x of f, which is 1 over 2 pi omega minus infinity to positive infinity x of omega e to the j omega t dw. All right, so this is another way of looking at it, the definition of Fourier series and Fourier transform in terms of omega. So this is your Fourier transform. And this is your inverse Fourier transform. Now, you might be wondering, where do I get that 1 over 2 pi? Where do I get that 1 over 2 pi? Because it was not there, but in omega it was there. Why? Because let's look at it. Omega, because we have it in terms of dw. So omega is 2 pi f. So what is going to be dw or df is actually going to be dw over 2 pi, isn't it? I hope you're getting it. So if I were to take an integration of this, so df is going to be dw over 2 pi. That's why I have, in order for me to replace this with dw is actually, because in the actual equation it was df, wasn't it? So I need to have it in terms of d omega, and in d omega is actually what? 2 pi times df, or in terms of d omega, this is going to be 1 over 2 pi. Because I'm making a replacement here. In my actual equation, this was actually, so this is the definition of Fourier transform in omega domain. This is an inverse Fourier transform, and this df is being replaced because here we have d omega, and d omega divided by 2 pi would actually give me df. That's why I have 1 over 2 pi outside. So this is how you drive a Fourier transform, the equations of Fourier transform using Fourier series, making it a periodic extension of a signal. If you have any questions, please leave it in a comment section, and don't forget to subscribe to my channel. We'll be making upcoming videos on Fourier transforms and other things like that, some example of Fourier transform.